everyone. So today we have the second talk of Youming, and this time about graphs and matrix spaces.
Thanks. Yeah, thanks all for coming. So today I'm going to change gears from last week talk to matrices and graphs. And it's more like, I don't know, this is a more combinatorial, and though of course there will be algorithm complexity. So yes, so for basically I'm going to talk about the so-called matrices and graphs, and in the abstract of this talk, I mentioned that 4 years ago I will give a talk on linear spaces of matrices, which is a great talk. And this talk basically is kind of like offering another viewpoint to study matrices, matrix spaces, kind of in analogy with graphs, but things will be different when we go to the linear algebra world, and we will see the new phenomenon or phenomenon, but also graph theory being a very useful lead into questions and connections on various methods. So yeah, I'll start with setting up some notations. So this will denote, the n will be a natural number. So this will be 1, 2, 3. I will be mostly looking at bipartite graphs on the labeled vertex sets. So bipartite graph in this talk will be on vertex set. Vertex set n cross n. Okay. So namely left vertices label from 1 to n, right vertices label from 1 to n. So it's essentially a bipartite graph, it's just a subset. This is just the edge set, right? So then for general graphs, I will be looking at undirected simple graphs. On vertex set, just n. So such a graph will be denoted by just a subset of n choose 2, the set of size 2 subsets. So this is a bipartite graph and a general graph in this talk. And then about matrix spaces, right? So matrix spaces is a linear space of matrices. So I will do a matrix space. Will be denoted by this script M, which is a subspace of M, N, F. So this is the linear space of n by n matrices over a field F. And then I will also be caring about the so-called skew symmetric, just like anti-symmetric, like from yesterday's talk, skew symmetric matrix space, which will be a subspace usually denoted by script A. This is lambda nf, where lambda nf denotes, this is the linear space of n by n skew symmetric matrices. Matrices over a field F.
What's this?
Yeah, anti-symmetric or skew symmetric basically mean that A equals minus A transpose. Symmetric A equals A transpose, right? Skew symmetric just means there's a minus. Okay, so essentially, I'm going first to give you an idea, how to embed graphs into matrix spaces. Okay, so essentially here, if you look at, for example, one edge in the bipartite graph setting, then you can build the so-called elementary matrix, right? So there will be a matrix called elementary matrix called EIJ, which is just a matrix with ij entry being 1, the rest being 0. So this is the elementary matrix with just one entry being 1, the other being 0. Then if you have an edge in the graph setting, then you can build the so-called elementary skew symmetric matrix, Hij. Then it will be the skew symmetric matrix with the ij position being 1 and the ji position being -1, the rest being 0. For example. Okay, so now given this, simple constructions, now of course, if you start with B, which is a bipartite graph, which is a subset of important, you will build the graphical matrix space corresponding to B, which is MB, which is the linear span, as you can imagine, of EIJ, where IJ is in D. Right? And if you have G, which is a subset of n choose 2, this is the edge set, right? Then the corresponding skew symmetric matrix space will be the span of AIJ, where IJ is in G. Maybe it's illustrative to give one small example. For example, if you have, say, a bipartite graph, I don't know, with these edges, then your left vertices will be left from labeled from 1 to 3, right from 1 to 3. Then the corresponding matrix space will essentially consist of those 3 by 3 matrices, where you check, right? If it's 1, 1 position, then you can do arbitrary thing here. 1, 2 arbitrary, 1, 3 no edge, so it's 0, right? So similarly, 2, 1, 2, 2, 2, 2, 2 is 0, 2, 3 is there's the edge arbitrary. So for 3, then there will be 3 mapped to 2. So then the corresponding, given such a bipartite graph, the corresponding matrix space will consist of those matrices with these entries being 0, the rest can be arbitrary. Then the skew symmetric will be similar. If you want to draw a very small example, it can be something like this. Maybe this, right? To make it non-bipartite. Then the corresponding AG will be, first is skew symmetric, diagonal must be 0. Then
it's a field of characteristic too.
Yeah, right. Actually, I would like to use alternating so that you don't have this characteristic 2 issue. But alternating seems a little bit, unfamiliar.
Okay.
Yeah, so I use skew symmetric. But if you use alternating, then
What's alternating? Sorry.
Alternating means that so I could have used, for example, alternating, which just said that a matrix A is alternating if for any vector V in F to the N, we have V transpose AB, this is a bilinear form evaluating on the 2 vectors is 0. So this will be alternating. Then you don't have this characteristic to each. Yeah, thanks. So, okay, then for this general graph, the corresponding skew symmetric or alternating matrix space will be A. Then if you have A here, then you have minus A here, right? You have B here, minus B here, C minus C here. So this is the, starting from graphs, bipartite graphs or general graphs, you can embed into matrix space or skew symmetric matrix using these elementary matrices or skew symmetric elementary matrices. Okay, so this is just to give you an idea. We are going to connect graphs into matrix spaces, and this is essentially the embedding from graph to matrix spaces. And what I'm going to tell you is that there are some interesting stories, hopefully. So we are going to see some correspondence of graph structures to matrix space structures. So for example, the graph structure here will be there to people in combinatorics will be, for example, perfect matching. Right. Or independent set. Or expander. Or connectivity. Or cyclicity. and so on. So the list goes on, it's we are building the list. It seems to be that for many of these graph theoretic properties or structures, we will have some correspondence in the matrix, on the matrix side.
Maybe one should stress that on the matrix space side, these were just examples, but we can consider all matrix space,
Exactly.
not just
these
that
ones.
look like this.
Yes, not just this one. So you can see that these matrix spaces, they are special matrix spaces, right? They are, for example, spanned by rank 1. They have a basis of rank 1 because EIJ is rank 1, right? AIJ is rank 2. So these are special ones, but we can when we go to the matrix space side, we will be dealing with more general matrix spaces. We will see new phenomena and so on. So, and yeah, based on the feedback of my last talk, I realized that I probably could not accommodate talking about all of this. So I will just focus on these two for this talk, but I hope that I will give you some idea that this seems to be an interesting direction to look into. Okay, so that's the plan. So let's start with the first one, perfect matching side. Okay. So, and for this part, I will be mostly looking at bipartite graph. So recall that just as we have been doing there, right? Starting with a bipartite graph B. I build this MB, right? MB, which is the subspace of MNF. For this part, for the perfect matching part, I will, for simplicity, I'll be assuming that F is large enough, say larger than 2A. This is kind of a technical condition, but it's without loss of generality. Okay. So the first connection between graphs and matrix spaces probably goes back to Tutte, Edmonds, and Lovász. Give the following, fact or observation that is, well, maybe it's a theory, but so Edmonds, Lovász. We show that B has a perfect matching if and only if MB contains a full rank matrix. So this is the first connection between graph property and matrix space property. So, perhaps I'll give a quick short proof of this so that you get the idea of, this truth. So B has a perfect matching, right? Let's, we want to prove an even only. So let's look at this B, which is the perfect graph. So maybe we assume that B has the following edges, right? E1 up to En. Where every EI is an edge, so it's just, SI. So this is the left vertex, this is the right vertex. Now we build, for simplicity, right? For simplicity, we call EI to be the elementary matrix for this corresponding to this edge. This is the elementary matrix with SIT isolation being 1, the rest being 0. So now I know that, for example, MB is actually consists of all the linear combinations of these EIs, right? So MB consists of AY, EY plus AM, So this is MB, contains all the linear combinations of these elementary matrices. And now, what I want to do now is basically to introduce some variable set. So maybe I'll go here. So I'm in here. So I will construct now I'm introduce x1 up to xm, they are variables. And then we'll consider xb. So xb will be essentially just x1, e1 plus xm, So what is XB? XB is essentially this matrix where the ij position is xk if ij is an edge, and 0 if otherwise. Okay. So now it's a matrix of variables. And then I would like to consider determinant of XB. Okay. The determinant, of course, by doing you have a summation over the permutations, you have the sum, you have the monomials, you have the monomials being XB, you have the product of the permutations of I sigma. This is a definition of expanding according to the determinant. Now you say that every monomial in the determinant essentially corresponds to a perfect matching, right? Because essentially this sigma is defining how the permutation is doing, whether it has a perfect matching or not. So now you have the observation B has perfect matching if and only if determinant of XB is not a zero polynomial, right? Inside this polynomial ring x1 to xn. But now, because we assume that field is large enough, non-zero polynomial means non-zero function. It's a non-zero function means that here we use f is large enough, and the so-called Schwarz-Dipole lemma, and now people say it should be called polynomial identity testing lemma. Polynomial identity testing lemma. We are over large enough field, non-zero polynomial means non-zero function, so there exists A1 up to AM such that A1 E1 plus AM EM is run.
So what's the precise statement of this lemma?
This precise statement lemma says that. Well, you can also use combinatorial data sets. So this polynomial identity testing lemma is saying that suppose f in x1 to xn is non-zero polynomial. Degree of f is d. Then the probability of, if you sample A1 up to AM from some set S, S is a set of field elements. So S is a set of field elements. Say S is larger than 2n. Then the probability of F evaluating on A1 to AM is non-zero. The probability should be larger than 1/2. It's n over d, but I assume that S is large. But essentially, this is just saying that for polynomials, if it's a non-zero polynomial overlapping our field, then it shouldn't be.
What is n actually? N is the n.
Sorry, m. Yeah, m. I should really say d. Sorry. D. There's no n here. Okay. Sorry. This is a Schwarz-Dipole lemma. Okay. So now you say, so the first connection, right? E has a perfect matching if and only if MB contains a full rank matrix. Yeah.
If you have a matching that's maybe not perfect, it has k edges, does it mean that you have a rank k maybe?
Yeah, exactly. We do have. Okay. Okay, so now, given this connection, you may wonder, Tutte, Edmonds, Lovász, they are like pioneers of graph theory. So why do they consider this, right? So essentially, the Tutte considers this. Actually, Tutte considered this in the general graph case, namely, Tutte considered the general graph. And he used this connection between general graph and this AG, whether it has a full rank using Farfan and so on. So it gives the first characterization of graphs without perfect matchings. characterization of graphs without perfect matching. So that's what Hart did in the 1940s. So the first such result actually comes from this linear algebra characterization. Then Lovász was interested in the algorithm aspect. Lovász asked, okay, so because you can see that given this connection, to test whether a bipartite graph has a perfect Choc matching or not, goes to check whether a matrix space contains full rank matrix or not, right? And you can see from this polynomial identity testing lemma, essentially, if it contains a full rank matrix, then by doing a random linear combination, it should give you one, right? So Lovász was interested in the randomized algorithm. That's in the 1970s. And very interestingly, Edmonds in the 1960s, he proposed a question that is, look, this MB, right, as we were suggesting, as Abby was saying, this is a special type of matrix spaces. So what about general matrix spaces? Can we still do that? You can see that for general matrix spaces, you can still do this polynomial identity lemma still holds. So you can still do random linear combination. But then the question is, of course, so general Edmonds asked for general matrix spaces. And of course, now for which we know there is this randomized algorithm. The question,
So what is the question for the general matrix spaces?
yes, so the question is, can we get deterministic, right?
For what?
For okay, so I'm about to say that. So now the question is, give a deterministic polytime algorithm for testing if general matrix space, right? General matrix space contains a full rank matrix or not.
General matrix space is given by a basis.
Basis, exactly, yes. Contains a full rank matrix or not.
Before deterministic, so the randomized is obvious.
Yes, by this polynomial identity testing lemma, if it has a full rank matrix, then you do a random linear combination with probability at least 1/2, as long as you are sampling from the field that you have enough many field elements. You do the sampling, do a random linear combination. Then with probably 1/2, right, you get a full rank matrix.
I mean, here, the linear combination was for elementary.
Yes, for element, this is for this special matrix
You're saying
spaces.
no matter what the basis was.
No matter
Given
what.
some basis.
This is one question, but still related to this MB, right? But here we are looking at general matrix spaces, and maybe I'll finish this
How are they described?
by basis, linear basis.
Oh, okay.
Yes. Full rank matrix space, matrix. Where this M, is a general, doesn't necessarily come from this, and is given basis, for example, A1, AM. Now A1 to AM are arbitrary matrices.
So can we,
Can we do that?
suppose you're given a basis?
Yeah.
You're saying the randomized algorithm is to
Do
put
it.
a variable for every coefficient,
Yes. And
take a random linear combination.
yes. Okay, so I'll elaborate on this part. This proof
You're
is
saying
okay,
the same thing, the same proof kind of holds a determinant. Well, not the same in the coefficient.
Yeah, maybe I'll elaborate on this part. The proof is okay, right? So I just erase this part. Okay.
You may be more familiar to some people if you just think of the matrix space as it is given by a matrix whose entries are linear forms in the variable. And you ask whether the determinant is a polynomial in these variables is identity still. It's just the PIT problem.
Okay.
This is this
Okay. So maybe-
by variance reduction, it's general PIT problem.
So I'll maybe make it more elaborate. So M is a matrix space is given to us by a basis, linear basis, A1 through AM. So which is a subspace of F. But from the algorithm viewpoint, we are just looking at this M and N matrices, right? So now the question or output will be yes, if there exists A1 to AM such that the linear combinations, right? A1 plus AM is 0. And of course, no otherwise. We are assuming that field is large enough. So given this problem, a randomized algorithm will go as follows. So you go to the randomized algorithm. Will go as you randomly sample each AI randomly from the field F, maybe a subset of the field, which is large enough. Then do a linear combination, right? If it has if indeed M contains a full rank matrix by polynomial testing lemma with probability at 1/2, you will get a full rank with such a random linear combination. If it doesn't have any full rank matrix, of course, any linear combination won't give it, right? So this is like the RP or co-RP, depending what side you're looking on. This is the RP algorithm. So now the question is, can you give a deterministic algorithm?
In the trigger algorithm, what's the running time of the trigger algorithm here?
Exponential, right? So actually, we don't know any sub-exponential. Any sub-exponential improved to sub-exponential will already have major consequence. Okay, so let me now talk about the consequence. Okay, so the consequence for this problem is that this is a major theorem by Habanes and Padillaro. That is, if you can give a deterministic polynomial time algorithm for this problem, it will imply lower circuit lower bounds. Okay. The randomization for this problem will yield circuit lower bound. Well, it's a the specific form of the circuit lower bound is a little bit funny. It's like either you get arithmetic circuit lower bound or you get Boolean circuit lower bound, but in either this lower bound is like seems very difficult for current techniques. That's probably fair comment. So now you see that starting from this connection, then is of course we have all this background, and then now if we go to the question of asking general matrix, what would happen for general matrix spaces, then you will get some, serious consequence from the.
I thought there is this result of the Roy-Mashuran that says that if the rank of the space of the matrices is large enough, then you have a matrix of high enough rank. Isn't that, doesn't it solve this?
Yeah, there is. No, it doesn't solve it at all because nobody guarantees to you that the dimension is large.
Right.
But it's how you test, you check the dimension.
No, the dimension.
Dimension M is our, yeah.
It's not
Not
even-
even, if the dimension is bigger than n squared minus n huge, then you must have a non-singular matrix. But I give you 10 n matrix.
Actually, I'm about to talk about this.
Okay.
So yes. Okay. So, okay, now I guess this is going to give us some motivation, right, to look at matrix spaces in general. So now I want to
If anybody saw this way or Mishram or anybody else, then it means pretty different.
No, I understand, this is why I'm
So,
like,
yeah.
no, but I understand, I think his result is tight, but
Yeah,
it just.
we were talking about,
Yeah.
but
No, I now understand why it's tight and still the.
it's a very Yeah, it's one directional in very special case. We know the answer without an algorithm.
Okay.
So now we really want to, for example, if you want to look at the circuit lower bound form and so on, Avi gave the talk 4 years ago, so you can go watch Avi's talk to see how the circuit lower bound goes and how it relates to valence theory of permanent and determinant and so on. But here, Avi already talked about it, so I just go to the next topic, that is for convenience. Okay, so we just say that a matrix space is singular if it doesn't have full rank matrix, doesn't contain matrices. Actually, from the combinatorial in Pagliazzo, actually to understand the structure of singular matrix spaces, or if you have a way to certify if a matrix space is singular or not, it's more like putting it this, asking if you ask whether a matrix space is singular or not, can you give efficient witness that already it will not give you a circuit lower bound. So we want to understand the structure of singular matrix spaces. And here then comes a very very natural question, that is, what is a max dimension of singular matrix spaces? So we want to know, in terms of dimension of the matrix space, how large can it be? And you can probably, you think a little bit, then you can probably say that, okay, here is a matrix space, which is singular and seems to be of very large dimension. So namely, every entry is arbitrary, and except that the last row is set to 0, right? So this is a matrix space, and you can say that the dimension of this matrix space is n times n minus 1, right? So you can go as large to n times n minus 1. So now the question is, can it go larger, right? Can it be even larger than n times n minus 1? So then here comes a very classical theorem by Youming. Which basically said that this is tight. So the max dimension of singular matrix spaces is equal to n times n minus 1. So this is the Youming result, and then it will be generalized and improved by Flanders and Mechelin. So okay, so this is nice. We know that from the dimension viewpoint, if you go beyond n times n minus 1, you will get a matrix space with full rank matrix.
What's the improvement of?
Okay, so you can consider singular is of max rank smaller or equal to n minus 1, right? Then you can consider rank bounded matrix space. Namely, the max rank is at most R. That's Flanders' result. Then Mechelin then come at Flanders needs some condition on the field. Field should be large enough, then Mechelin get rid of this field constraint. So that's the Youming, and then we could ask the following. So remember, we have this connection, like B and MB. From a biparallel graph B, we have this matrix space MB. Now, the question, then we can ask a generalized question here, that is, max dimension of singular matrix spaces. Now it's now contained in the full matrix space that contained in MB. Okay, so we are putting some, we are saying that some position of the matrices must be 0, essentially, right? This is the condition given by this bipartite graph B. So if B is complete bipartite graph, then, this is essentially the domains. Then goes back to the domain. Okay, we can ask you this question. That's the question we consider in the joint work with Avi, Yovo, and Ina and Kanxi. So we can show the following connection. So I view this as strengthening the connection between biparallel graphs and matrix spaces. So the max dimension of singular. So this is the important phrase. So the max dimension of singular matrix spaces contained in MB is equal, as you can imagine, right? We are going to talk about the graphs, right? This matrix space is equal to the max size of subgraphs in B, contained in B. Sorry, max graph of without perfect matching. Without perfect matching in B. So this is when we have B being a complete biparallel graph, it covers the dominant result. So this is just saying that if you have some support constraint, namely which some matrix you set your matrix to be 0, you are interested in the max dimension of singular matrix space contained in such matrix space, then basically it goes back to the graph problem, right? You're basically asking for the max size of subgraphs without perfect matching.
So that subsumes the
Assume what?
Subsumes the donor, yeah.
Yes, subsume the
The special case. The special case in the
complete.
donor is the maximum number of edges without a perfect matching in a biparallel graph is when you have an isolated one.
And these are the only solutions, or?
Yeah.
Yeah, question, please.
What if you maybe restrict to rank, like in K singular if you don't?
Yeah, if it max, we also have that, yes. Yeah, it can be generalized to that setting. And I should also say that actually the K lemma is from mesh length. So there's the K lemma by mesh length in the proof, but I won't have time to go into the proof.
Can you say just a couple of sentences like that?
Yes, so you can imagine for this type of thing, usually one direction is easy, right? So usually going from graph to there, it's easy. But the tricky thing will be if you have a singular matrix space in MB, you can imagine that this may not be really in a nice format corresponding to some graph. So what Metrolam did was a very clever idea, namely you have some matrices, right? Even though they have in MB, they may not be rank 1, for example. But then you can choose some clever basis of that. So suppose you have some singular matrix space C here, which may not be be spanned by rank 1, but then you can choose a clever basis of C, and from that basis you can recover this graph. So that's what Metrolam did. And this basically also corresponds to something like the minimum number of lines and rows and columns to cover, for example, matrix space and so on, non-zero entries in matrix space and so on. Okay, so good. So I think, yeah. Now, I would like to, again, let's change gears and think about this thing. Another thing that you are very familiar with, Paul's theorem. Okay. Paul's theorem, of course, is saying that if B is a bipartite graph, then we know that B has perfect matching if and only if B has no so-called strong subset. And what is a strong subset? So a strong subset is set of left vertices, such that because it's a bipartite graph, right? So for left vertices, its neighbor is on the right. So NL is the set of neighbors of L on the right. And we see that L is a shrunk subset if the size of L is larger than the size of its neighbors on the right. So this is what can call shrunk subset. Maybe some people will call it Hall's obstruction or something. So this is a Hall's theorem, right? It gives a characterization of bipartite graphs without perfect matchings. This is the main reason, right? This is the reason for a bipartite graph to have no perfect matching. Now we can define something similar in the matrix space setting. So in the matrix space setting, we are going to define an analog of shrunk subset, and which we will call it shrunk subspace. That is given B F, then U, which is the subspace of F to the N, is a shrunk subspace of B. Maybe I keep using M. Is shrunk subspace of M if there exists V, which is the subspace of F to the N, such that for any matrix B in N, E will be mapping U inside this B. So this is a shrunk subset, a subspace, which is saying that there exists a subspace of F to the N. If you look at the image of U under every matrix B in M, dimension of U larger than the dimension of B. Yeah. So it's kind of shrinking this U into a smaller dimension B. Okay. And that is by doing some change of basis on the left and on the right. So your M by basis changes, your M will be of this, every matrix of your M will be of this form. And then there will be U, this will be corresponding to B. There will be a large block of zeros. And this larger block of zeros will be invading into the diagonal, which is suggesting that this dimension U is somehow compressed or shrunk into this smaller dimension V. This is a shrunk subspace. But of course, it is by basis changes because U may not be stand by the first standard basis vector. Well, I should precisely should be contained. Okay, so this is a shrunk subspace, right? And you can also see that if a matrix space admits a shrunk subspace, then it must be singular. Because every matrix in the space M will be of this format, right? It has to be singular. So this will be a singular matrix space. And now here comes we also want to build connections, right? So this is some connection which is kind of evident in the literature, but probably not really written somewhere. That is, B has a shrunk subset. If and only if MB has a shrunk subspace. So that's another connection, right? So this is connecting shrunk subset, graph-theoretic structure, to shrunk subspace, which is matrix space structure. Okay, so I'll do a quick proof of this. Actually, it's kind of easy because but also to give you an idea of all these things, how these things go usually when we are planning to build these correspondences.
So is this equivalent to the vector condition that every B shrinks U, or?
Right, I probably shouldn't be using B because. Okay, sorry for the confusion. Yeah, so let's call it A. Right, any, yes.
So you can just say that every A shrinks U, not to the same V. Is it equivalent or?
No, you want the same U and V.
We want.
Yeah, no, I think it's equivalent.
We want essentially this is saying that there is some target, right, V, which holds for every A in M. Every A in M should send U to this smaller dimension V. This U and V is with respect to, which is not like for this A, you have some V corresponding to A. For that A prime, you have some V prime. It's not like that. It's
not equivalent.
Imagine basis of rank 1 matrices. Each rank 1 has such a V.
Yeah, actually, if your M at meets a rank 1 basis, then it's kind of equivalent. Because what you were suggesting is basically saying if it's A is not full rank, right? It will definitely compress, for example, the full space into some smaller space. Right, but here we are saying that this choice of V is uniform across the choice of. So for this direction, right, we start with B, which has a strong subset. So suppose L is a strong subspace. And then, of course, L consists of several vertices, right? Say I1 to, I don't know, Ik, which is a subset of it. Then you want to build a strong subspace. But this is usually the natural step, right? You essentially take the coordinate subspace corresponding to this. So you look at the, I don't know, S, which is a span of EI1 up to EIK, where EI is the element in the standard basis vector, which would be a subspace of F.
Probably want to call it U, no?
Oh, right. Okay.
This S is U.
This one, yeah, good. Yeah, thank you. Yes. Yeah, that's. Okay. So you can basically verify that this gives you the strong subspace when you look at the coordinate subspace bounded by the coordinate. This direction, we are going to cheat a little bit. That is, if we're basically going to show that if B doesn't have strong subspace, a subset, right? Then we want to show that MB has no strong subspace. So we start with B, but if B has no strong subset, then it has a perfect matching, right? So B, now we look at the case of B has perfect matching. If B has perfect matching, then MB contains a full rank matrix. We know that, right? So MB has full rank matrix. Then it cannot be because if it has full rank matrix, it cannot have a strong subspace because strong subspace means that MB will be singular. So cannot have a strong subspace. Okay. So far so good. So okay, so now we have another correspondence of the structure. So the question, of course, is then we have Paul's theorem in the graph settings. Would something like that hold in the matrix space setting? You can imagine that is, if you look at the all bipartite graphs, Paul's theorem is saying that we can divide them into two classes. Either they have perfect matching, or they have strong subset. On the other hand, if you look at all matrix spaces, then because then kind of we have either it has a full rank matrix or it has a strong subspace. So if there's nothing in between, right, then we'll be really happy. But the unfortunate reality that there exists something in between, that it doesn't have full rank, which means that it's singular, and it doesn't have strong subspace. So that's kind of unfortunate, because if there is no such bad guys there, we would have solved something. And an example would be, it's actually not very hard to find. Just look at this skew symmetric 3 by 3. Look at this matrix space, 3 by 3 skew symmetric matrices. And because it's odd size, right? It's 3 by 3, so it doesn't have a full rank matrix. On the other hand, it's not very hard to verify it doesn't have a strong subset either, subspace either. So this is the naughty stuff inside here. We know of several families from different sources like algebraic geometry and so on. So there are bad guys here, which kind of prevent us of doing something or circular about kind of.
Very well. So if this was not the case, why did you say you would solve it?
That's what I'm going to tell you. So we know how to test whether a matrix space has a strong subspace or not, deterministic polynomial time. So that's what we're.
So this gives a solution for the graphs, or
yeah, this for the graph here we don't have this problem, right? This naughty stuff.
But was it known before for graphs?
For graph is easy because it's not it's classical, right? The Hungarian method, alternating paths and so on. So it gives
An
you
algorithm to test if a graph has a perfect
matching
matching has been known
Okay.
like for hundreds of years, maybe.
So now I want to explain to you that we do have some interesting progress. But
Wait, sorry. Why is the skew symmetric an example of something in the middle?
first I mentioned right because it's skew symmetric, it has rank must be even, right? Its rank is max rank must be even. So it's 3 by 3, so it means that it cannot have a full rank because full rank here means 3, rank 3. But it's skew symmetric, so its rank is basically 2 or 0. And you can verify, well, it's a small example, so you can certainly verify after some calculation that it has no strong subspace. Okay, so again, we are going to kind of repeat the story. That is, we saw that in the matrix space setting, we have this connection between perfect matchings and full rank matrices. Then, then we look at the general matrix space case, and we want to know whether a general matrix space contains a full rank matrix or not. Now, the same, we can repeat this pattern, and then we can ask, given a general matrix space, does it admit a strong subspace or not, right? So here is the question. Given M, which is a general matrix space, does M admit a strong subspace? This is an algorithmic problem now, right? So you want to know whether. And that's basically, what Avi and we worked on like from 7 years ago, kind of 7, 8. It's almost 10 years ago. Yeah, 10 years ago. So the answer is that yes, it's indeterministic polynomial time. And first by Gard, is Oliveira, and then this is their work over, for example, hyperrealistic visual field. And then This is over, essentially over any field. Then very recently, there's another algorithm by Hamada. Well, I think their result actually
It's
was,
not very recent,
Yeah.
it's about the 17, I think.
yeah, they had this result, but somehow they only got published in Hamada and Hira. It's also over in the field. So there are now 3 algorithms for this problem. And this algorithm essentially is based on the so-called scaling idea originates in the average paper, an analytic algorithm for perfect matching. And then with Natilino and Smolensky. And then Guvis found a quantum generalization. And then in this paper, they show that that technique can basically solve this problem. It's like optimization over Riemann manifold. Of course, Avi has several talks on the online, so you can watch that. Our result is based on a certain type of linear algebraic analog of alternating paths method. I can explain to you this method a little bit later. And this Hamada-Hira result is also very interesting. It's based on optimization over the so-called cat-zero space, which we had this what is seminar last week about cat-zero spaces and so on. So it seems to be, suggesting that it's going to very diverse mathematical
They
areas.
went to cat-zero spaces and their goal was this problem?
Yeah, yeah.
People do optimization of a cat-zero spaces. There are techniques. They are using a particular algorithm for optimizing certain functions with some structure over cat-zero spaces, and which some of them beautifully extend the idea of Lovász extension of some modular function.
Then,
It's an amazing paper.
then it's not just a modular over, Boolean lattices, it's modular over subspace lattices, which will naturally lead to the cat-zero spaces and so on.
Question.
Yeah.
Do all these also apply to the setting where one asks, does M admits a shrunk subspace of size up to K?
Yes. This one first, I think there's the extension, right, of this scaling approach to compute this, the shrunk discrepancy also. Yeah. Okay, so maybe we'll have a 5 minutes break. I'll come back and. Okay, so I basically now want to tell you this one. For both this work and this work, you can find recording on the internet. For this one, probably not yet. So yeah, I just mention this. So this is actually, if you look at this, it's a kind of very natural generalization of alternating paths. So let's review a little bit. Okay, so the alternating paths. So suppose you have a bipartite graph, and then you have a this is an edge set, this is a matching. Your question is, of course, whether M is maximum size or not. So question is M maximum size.
No, if M is given, it's not an interesting question.
It's a matching, it's not a max. We don't know it's maximum or not.
Is a larger matching.
Right, there is a larger matching or not, right?
Yeah.
And because of Hall's theorem, asking whether M is maximum or not is essentially asking whether there's a shrunk subset of the right discrepancy. Right? So this is the same as asking that there exists S, which is the sub L, which is such that the discrepancy between the size of L and the size of neighbor of L is equal to N minus the size of the current given matching. This is like the discrepancy, right? So this thing can be tested using alternating paths. So essentially, you have the left vertex set. You have the right vertex set. Here I'll use some colors. So Then you have some, without loss of generality, you can put your given matching M as, for example, just connecting this, right? By permuting the left right vertices. You can assume that your M is given like this, right? Connecting 1 to 1, 2 to 2. So these are the matched vertices on the right. These are the unmatched vertices on the left. Okay. So in the algorithm, usually, of course, we usually talk about single alternating paths and so on, but in the algorithm, it's usually more efficient to start with all the unmatched vertex and look at its, you then use unmatched edges to look at its neighbor, right? So the unmatched vertex, unmatched edges, say these are unmatched edges. Look at its neighbor. Of course, if its neighbor contains some of the unmatched vertex, we are good. So the tricky business is, namely, if when we need to go for a few more steps, will be the neighbors of these unmatched vertices will be contained in the image or in the matched vertices on the right. So if this happens, of course, what we want to do is to use these ones to go back, right? It's alternating. So unmatched and then matched go back. Then of course we may want to look at now we have more vertices on the left to start with, right? Now we use again unmatched vertex edges. For example, to go to the right. Maybe at this step we still haven't reached any unmatched vertices on the right, so we still need to go back. Maybe at this step, we are lucky, and then we find something. From we'll go step one more, go back one step, one more, then maybe we find an unmatched vertex on the right. So this is what the alternating path method is doing. And now I'm going to show you that.
So if people haven't seen, then you swap on this path. You swap matched and unmatched edges, and you get a lot of
matching, right? So here there are basically two possibilities. That is, if we can reach unmatched on the right-hand side, then you can basically increase the matching size. You find an augmenting path and you can increase the matching size. If you somehow, after several rounds, you find that you are trapped inside the matched vertices on the right, so trapped on the right. Namely, you cannot touch unmatched. Then you can find this so-called weakness for your maximality of your matching. Then you have this strong subset weakness with the right discrepancy. Okay, so this is the perfect matching case. Or maximum size matching case. Now, I want to basically show you that the same thing. The idea, well, is kind of like in a matrix space that is similar. Okay. So now we are given a matrix space. We are also given a matrix A inside this matrix space. Now the question is, does there exist a shrunk subspace with the right discrepancy? Such that the dimension of U minus the dimension of MU, I'll define MU later, equals the co-rank of A. Co-rank is like the discrepancy, right? Now, co-rank is just N minus the rank. So let me define MU. So given MU is essentially defined by the span because M consists of many matrices, right? It's a matrix space. It's the span of AU or the union of A. So essentially, we are looking at the collective images across every matrix A in M of U.
Another use of the letter A. Use A.
Yeah, maybe I'll use A prime. Okay, so this is what we want, right? And now we are going to do something quite similar to this thing here. So we have the left side being F to the N, right? Because it's N by N matrix, and so map from F to the N to F to the N. Maybe I need to define one more thing. I need to define one more thing, that is, I need to define if I have U, which is, so this is definition. I also need to define for V, which is the subspace of F to the N. Because there you can say that I need to go from left side to the right side, but then I also need to pull from the right side to the left side. So this requires me to define something called the inverse image, which is also natural. So the inverse of A on U on V is the pre-image such that AU is contained in V. This is also natural, right? So here, okay. So now I'm going to do something very similar here. That is, I've given this A, right? I know that this A set up some connection between F to the N to F to the N. For convenience, you can even assume that your A is something like, you can assume your A is something like identity R, 0, 0, 0. This is without loss of generality. So now you look at the kernel. So kernel of A will kind of be the unmatched vectors somehow on the left-hand side. Then the right-hand side, you will have like the image of A, which is like the matched vectors on the right-hand side. So you want to do essentially some alternating work, starting from kernel of A, because the first step will be using the unmatched edges, and the unmatched edges are essentially contained in A, in M, right? So you use, what you do is use M, you apply M to kernel of A, to here. If you get out of F to the N, you get out of the image, you are good. Your goal is to kind of get out of the image of A. But maybe in the first step, you don't. If you don't, then you pull back using A to pull back. Because A inverse will always contain the kernel, right? So you go back. So this is A inverse step. Now, of course, we want to iterate this process, basically. Apply M, A inverse to get back, and so on. So maybe the second step, we don't really get out of image of A, then we pull back. And then maybe in the third step, I don't know, maybe we are lucky and then somehow get out of the image of A in the third step. So in other words, this process is you start with kernel of A, you apply M, which is defined here, right? Then you get some V1, then you apply A inverse, you get back, you get U1, and here we want to check whether, at V1 we want to check whether it gets out of the image, right? Image of A. If V1 contains the image of A or not. If not, then we will show you, essentially then we will have found something like that. We will be good. So if not, then it's like we want to increase rank, but that's the tricky business. So here in every step, essentially on the right-hand side, we want to test whether it contains an image of A or not. If not, then you go back. You use A inverse to pull back, and then do another step, and so on. Then we want to know whether V2 is contained in the image on A or not. So this is like you can see that the idea is from the above here and here is quite simple. Now, here is a lemma that tell you that this kind of like a wishful thinking, right? We're just mimicking alternating paths in the linear algebra setting. So, but it makes sense because of this lemma with Haber, Karpinski. So the first thing to notice is that you will essentially have V1. V1 is always on the right hand side, right? This is V1, this is V2, and so on. So you will have V1. You will first be strictly increasing, then up to at some point you have VL, and then you start to stabilize. So this is like first observation. The second thing is that, then look at this stabilized vector space. VL is contained in the image of A if and only if there exists this. There exists a shrunk subspace with the right discrepancy. So that's the lemma. Then you can say that, okay, this kind of gives you a hint, right? This is the right procedure to do. But there are two things, right? As we were saying there on the graph setting, so we do this, right? We do this iterative process. We call it one sequence in our paper. So the question, of course, then is VL at the limit subspace. If it's contained in the image of A, we are happy, right? We get the discrepancy and the shrunk subspace. So this is
the weakness that the rank cannot.
Right. Well, non-commutative rank cannot. Right. So this is good. So this part is the good part. But on the other hand, if VL is not contained in the image of A, then you would like think that we need to increase rank, right? Because rank is like matching size here. But in general, because of this failure of Paul's theorem in the matrix space setting, we cannot do that. So we cannot increase rank within M itself. So that's the tricky bit. Now, what do we do, right? So turns out that because of the invariant theory stuff, you cannot really increase rank within M, which consists of linear combinations of, if M is spanned by D1 to Dn, then you cannot increase rank within the just doing linear combination of D1 to Dm does not suffice. Okay, now here comes the good part. But we can increase rank when we look at the tensor product of M with some full matrix space. So then we need to kind of look at M tensor some full matrix space, say EF, which consists of, now it's not A1 to AM, now these AIs will be also matrices, D by D matrices. So for example, maybe I call it C1 tensor D1, Cn tensor Dn. In other words, we cannot find full rank. For example, if we want to know whether there exists does not exist shrunk subspace or not, we will want to find full rank here, but we cannot find full rank here, but we can find full rank in this tensor product space setting. So this is possible, and this is because of some reason from invariant theory. But of course, now the question is how large this AI should be, right? It's D parameter. Is this D parameter exponential? If it's exponential, it's probably not that helpful. So now the question. So because it's invariant theory, you need to go back to Hilbert. So here comes a question. How large would D be? And
Why should we believe that tensor will help you at all?
yes, this is because from invariant theory, all the matrix tuples with such a strong subspace is the so-called null cone of some invariant ring. And this invariant ring consists of basically the left-right action on matrix tuples. So then there's some characterization of the invariant ring, which is essentially of this format, which is suggesting that just looking at linear combinations of DI is not enough. But if you look at tensor product of these DIs with some matrix coefficient, then that gives you a full invariant ring. Right. So there is some invariant theoretic background.
A very loose intuition is that this question about the maximal nodes on a subspace or the discrepancy captures a non-commutative notion of prime.
Yeah, there's a
non-commutative. Determinant is a commutative polynomial. You want some analog, and just very intuitively, if you have a non-commutative polynomial, one natural thing to put for the variables is not elements of the field, but matrices. So it turns out that if you put matrices of all sizes, you will discover at some size, you will discover what's the rank is. So you put matrices to capture the non-commutativity of the variable. And what level will you capture it? This is in general an open question. And for this one, it's
Yeah, that's I'll tell you. So how large should this D be? If you go back to Hilbert, and then there are some, because Hilbert just showed that it's finite. So it's how finite that is a question. Then there's a Popov and Dirksen. These are very general results. They apply to any reductive group action, representation, and so on. So from there, you get something like 2 to the O(n) squared. Right? Then we have some result. We have some improvement, but it's not really, it's good improvement, but it's still exponential.
Factorial, right?
Yeah, n factorial. Then here comes Dirksen and Manton. I guess also we've contributed a little bit on this part. So they first discovered that. Then actually it can be brought down to N. So it's linear. So D just needs to be linear in order for this thing to capture this strong subspace business. So now this basically gives you a hint of this, how this algorithm will go. Because if it's containing in the image of A, good, we have found the weightings. If it's not in the image of A, we cannot increase rank in the original matrix space, but do the tensor product. Go to, these are n by, because of this bar, right? These are n squared by n squared matrices, which is not too bad polynomial, right? So you go there to find a larger rank in that setting, and then pull back and solve. So this is how our algorithm goes.
So you need to increase the rank every time?
Yeah, it's not
the sizes of the matrix.
The size and height?
No,
it's always n by n. Then you will find some. Basically, you will find some larger rank in this setting. But then you can go back. You can basically.
Okay, here you describe some kind of iterative
process. Yeah. So this is just for knowing whether there exists a discrepancy of this one, right? Maybe then you will find some, larger rank here inside this space. But then basically this will give you something to start with. You can bring back to your general matrix and then restart the process. So you don't need to do this every time you do this n times, then that will be too much, but you can go back.
You you discover something in the n squared dimensional space, and you can pull it back. I mean, the proof
the
such
original
as
space.
yeah.
I see.
Okay.
Out of the range you get are always multiples of this D. Always multiples of D.
Yeah,
And
that's
then-
another kind of magic there. This
Yeah,
involves
that's-
I mentioned to you this division.
It's a complex paper, their paper, they is telling you just bits from it.
Okay, so good. I think I talked, I hope that you find this part interesting in the sense that we start with correspondences and then look at general metric spaces, and then sometimes we bump into some deep stuff and make some interesting discoveries. So now I want to really, switch gears because I want to tell you about another aspects which may be more, interesting to our combinatorics audience. People audience, that is independent set and coloring, for example. Now we are going to change gears and consider general graphs. And we were saying that, okay, from general graphs, you can build this skew symmetric matrix space, which is the span of Aij, where, Ij is in G. So I assume that everyone knows the independent set. So I want to define some structure here, which is kind of like independent set space. So the definition is that now I'm going to define for general matrix spaces rather than just this H. Skew symmetric matrix spaces, yes. For A, which is a subspace, lambda NF, U, which is the subspace of F to the N, is a totally isotropic. For convenience, I just call it Ti. So it's a totally isotropic space for A. If for any U prime in U, and for any A in A, we have U transpose A U prime is 0. So in other words, a totally isotropic space is a subspace when you restrict every A in this alternating matrix space. When you restrict to this U, it should be a kind of the zero map. Because its zero map means that it's evaluating, it's the bilinear form, it's evaluating on two vectors equals to 0. So that is, I change our basis. Your A, every A in A should be of this form. So you have large block of 0. This will be your, if it's dimension D, then it's D by D, large block of this. Okay. So then similarly, you can define now if you have because from totally isotropic, we will think of it as an independent set. Then we will do vertex coloring, which, a vertex coloring will be basically a partition of vertex set into independent sets. We are going to do something here. That is F to the N, U1, UC is a CTI decomposition. So this is direct sum decomposition of A if every UI is a TI space. Now, I want to define two parameters related to this independence, totally isotropic space and totally isotropic decomposition. That is, alpha A will be the max dimension such that U is Ti for A. And this is chi, right? This is the minimum of C such that there exists C Ti decomposition for A. You know, for graph theory people, now you know what I'm going to do, right? So the theorem is A. That is basically these two things, right? Alpha G equals alpha AG and IG equals I AG. Okay, so if you go to the graphical matrix space, the totally isotropic number equals the independence number of the graph. The chromatic number of the graph equals the Ti decomposition number of the matrix space. Okay, so that's usually the first step, right? We are building this connection. This seems to be making sense. So now we want to look at, for example, this totally isotropic and Ti decomposition number as well. Okay, now I have a couple of things. I have like strengthened decomposition and so on, but because of time, let me discuss with you this thing that is the most interesting, I think, because it's kind of like the extremal and probabilistic graph theory put into this setting. But yeah, I think I have like 20 minutes. I'll use 10 minutes maybe to talk about the proof, right? Because the proof is really simple and give you an idea of how this connection goes.
So a quick question. Why do you call it totally isotropic?
Yeah, this is from the bilinear form type in this. From bilinear form, they have totally isotropic, and something called anisotropic, which is probably not a very good name. But basically, totally isotropic means that it's basically a large block of zero. And isotropic means that as long as you have U and U prime, which are linearly independent and you evaluate to zero, that's called isotropic. You have some, they exist like a zero evaluation. So that's called, I think I got it from Milner's book or something somehow. I just follow them just to avoid confusion. Okay. So I talk about the proof, which is simple. I'll just prove for the alpha. Okay, so first, alpha G is equal to alpha AG. Okay. So here, of course, you start with let S be an independent set. Now you probably are going to see what I'm going to talk about. You just take the coordinate subspace. So take the coordinate subspace of S. Now for the other direction, that's usually the more interesting part, right? So you take U, which is the subspace of F to the N, which is a dimension of U equals D, for example. A Ti space for AG. So what you are going to do is to express U by N by D matrix, and essentially the columns will be a basis of U. So the columns are a basis of U. But what we are going to look at actually are the rows. These are, let's say the rows are R1, R2, up to Rn. And because it's dimension D, we know that there exists a D by D submatrix is full rank, right? So there exists D by D submatrix full rank. And let this submatrix be, say, maybe the submatrix, the row indices will be I1 up to ID. Okay, so these are the row indices of this. Okay, so basically I'm going to claim that this will be an independent set. And you probably are going to say what I'm going to talk about. So claim S is an independent set of G. The proof is that if not, then there exists, I don't know, without the loss generality, this maybe I1, I2 is in G, right? If I1, I2 is in G, we know that this A, I1, I2, this skew symmetric, elementary skew symmetric matrix is in AG, right? But U being, because U is Ti for AG, so essentially it should mean that U transpose A, I1, I2, U should be the zero matrix of size DID. Because it holds for every A in AG, so we must hold for this matrix, particular matrix, right? But then we look at what this thing means. This essentially means that this basically just gives you R. This will be a row vector, so RI1 transpose RI2 minus, because this I1, I2 will be essentially taking the I1 row and I2 row and do something like this. I2 transpose 1 equals 0. But this is 0 if and only if they are linearly dependent. Right? These are two vectors, two row vectors of length d. But on the other hand, we assume that they should be linearly independent. So it's a kind of a very simple observation, just which contradicts the linear, full rank contradiction. Oh, good. So this RI1 is the RI1 is row, so this is the column. Our I1 transpose will be column. This is the row minus. So this basically give you, the other direction. So usually when you go to the matrix or the linear algebra setting, you have something a little bit more complicated. You need to think a little bit how to extract that graph-theoretic structure from this thing. And the chromatic numbers is essentially because of this one is essentially because of this and plus Laplacian expansion, because then you will have, matrices divided into several blocks or column part. You use Laplacian expansion to say that you have some,
What's Laplacian?
Laplacian expansion is, suppose, for example, first you have, let me just use 3 by 3. Okay. So maybe A, B, C, E, E, F, E, H, I, right? Then you have this determinant of this thing equals, A times this determinant of this submatrix and so on. So this is the row expansion, right, of determinant. But Laplacian expansion is essentially saying that you can do this blockwise. You can do this, you can look at this part, you can do the multiple row, you can have this block. Then the Laplacian expansion is saying that you can have summation of determinant of this thing with respect to this, and determinant of maybe some other columns, but with respect to the rest and so on. So I'm not explaining very well, but you hopefully get the idea. Okay. So okay. So now I want to. Here comes a very interesting question for me. Okay. So I want to somehow, given this connection, then it may be natural to think about some questions in the extreme or probabilistic setting. So here comes a very natural classical stuff from extremal graph theory, where people, I don't know, this is the Turan's number. This is basically Turan's classical result, but put in the independent sets regime. So this is the mean of alpha G, where G is n vertex and m edge. Okay, over all n vertex and m edge graph, you want to look at the mean of alpha G. So this is the Turan's number. And the Turan's number, of course, famously determined by Turan, which is, yeah, I need to check. I'm still having. Just check very quickly. N squared over 2n plus f. So yeah, but basically, if you don't see Turan's theorem put into this format, just trust me. This is definitely just a Turan's extremal graph theory result put into in the alpha m format. Okay, now you are probably going to see what I'm going to talk about in the graph in the matrix space setting. That is, right? We can define some number called alpha n m, but now over a field f. Then I want to examine the mean of alpha A, where A is the subspace of lambda nf, dimension of A is n. This sounds natural, right? So now we are not just looking at, alpha G, AG, but NA. But now the constraint is that the dimension of A should be n. Okay. So the question, and maybe I'll give you a little bit, example to just. So first, let's look at alpha n1 f. One means that we are just looking at a single skew symmetric matrix, right? If in the single symmetric matrix setting, then a single matrix, skew symmetric matrix, can always brought into some canonical form. That's classical linear algebra, that is something like this. Because its rank is even, so it's always, maybe the rank is 2R. If its rank is 2R, then you can always brought it to this format. Okay, so this is the alpha n1f. Because of this canonical form, you know that there should always exist some large totally-isotropic space. So it's essentially now this is an over 2. Now let's look at maybe alpha n2f. Now you have pairs of skew symmetric matrices essentially. Okay, so now you have A1, A2, which are both skew symmetric. And luckily, there's also some canonical form stuff going on there. It's more complicated, it's more like the Kronecker Weierstrass theory, but it's kind of classical, for example, Uranic goes down in they consider this. And basically, you can always brought this also into some zero block for both of them as simultaneous. So you can also brought a pair of skew symmetric matrices into this block 0, 2 blocks of zeros on the diagonal. This also means that the chromatic number here should be 2, right? So it's like you have, here you basically the chromatic number mean that how the minimum of C you can do this, right? So this here means chromatic number is 2 for a pair of skew symmetric matrices. So this also means that one of them is close to n-half or something. So this is also this. Okay. So yeah, so 1, 2, and 3 probably classical 19th century mathematicians have been considered, but interestingly, this has been studied in the context of group theory. So now probably I can tell you this theorem by or Shansky and Ruler, Harris, who proved that alpha n m f is less or equal to n plus 2n n plus 2. So you can compare with the Turan's number, which is very different behavior, right? For example, if m is roughly, I don't know, 2n, then it's already very small. It's like 2 or 1, or even 1. Sorry, maybe it should be the lower. Okay, so you can see that this has been studied. Actually, it's in the context of group theory. And now, then there is also only an upper bound. Now there's a very interesting thing in that if F is algebraic closed, then in this paper, they show that there's actually equality here. And both the upper bound and the lower bound proof techniques are very interesting in the sense that Turan's number, right, is proved in the extremal graph context. But this thing is proved using probabilistic method. And Lasse Piber told me, at least in one of his articles, he wrote that this is probably one of the first applications of probabilistic method in the group theory context. So this is upper bound is by probabilistic method. And then the equality part for the algebraic closed part is proved by intersection theory from algebraic geometry. This is probably by Harris. So this is the intersection theory. So I don't think
What's the relation to group theory again?
Huh?
I missed it. What's the relation to group theory?
Oh, the relation is actually, yes. So this is related to what I mentioned in the last talk is that this is essentially related to P group of class 1 exponent P. And the isotropic space there correspond to abelian subgroups. So of course, abelian subgroups are interesting, right, in the context of group theory. So yeah, that's why people got it is. Okay. So then this, of course, I don't have time to, the proof is not hard. It's like, I don't know, 10 minutes, but I don't think I have 10 minutes. But let me just mention a few things. There are several questions starting from this theorem. For example, this is we kind of, basically this probabilistic method basically goes by showing that a random m-dimensional subspace in lambda nf doesn't have a TI space of dimension of this thing, for example. So then this, we can ask for lower bound essentially, right? Lower bound for both probabilities from the probability or random graph theory viewpoint and extremal viewpoint. Because the extremal viewpoint is only known equality over algebraic closed field. Finite field, I think, is still open. And the extremal viewpoint. So this is one, I think, very interesting question. Another thing is that for people in extremal graph theory, there's also this generalization into hypergraphs, right? So there's alpha n m l, which essentially is asking for, this is after Turan proved this result. This hypergraph generalization becomes a very difficult problem. So alpha, I use H. So H is a L uniform. And vertex and edge hypergraph. And hyperedge. Right? This is a Turan's problem in the hypergraph setting. And this can also be generalized to the linear algebra setting by consider alpha n and LF. Okay, so what is the correspondence of hypergraphs in the linear algebra setting? Essentially, we are going to look at exterior products. So it will be something like alpha H, where H is a dimension and subspace of the L-fold exterior product for F to the N. Okay, so you see all the parameters there, right? So L here is the L uniform. Every set in the hypergraph is size L. Here L is the exponent or the exterior product you are taking here, and the size corresponds to dimension, and vertex corresponds to F to the N. So this
What's this? It's like a tensor product? What's this?
is a tensor product. Exterior product is tensor product, but modulo some relations. It's like a skew symmetric multilinear
Like you are allowed
functions.
to,
Yeah.
you're allowed to change the order of these.
Yes. So one thing to define is we think of it consists of all the multilinear functions but skew symmetric while alternating something. So it will be functions Fn equals Fn. L of them. So if L equals 2, it's just skew symmetric matrix or alternating matrix. And we satisfy the alternating property, namely if you swap two arguments, it changes the sign. If two arguments are the same, then it should evaluate to 0. Of course, there are some field characteristic issue I don't go into here. Okay. So this actually has been studied by L1. So in the 1990s, and they give a pretty weak bound here because the bound here is pretty general, applies to like combinatorial setting as well. So it's pretty weak bound. I think probably should some good bound could be put here. So this is there are like a couple of questions. Okay, one reason why this is reasonable is that there's also a connection between hypergraphs and these subspaces of this thing here. That is, I think I just mentioned this connection to give you just saying that it's not just bipartite graph or general graph, skew symmetric matrix space. It's also about hypergraphs and multilinear functions and so on. So the last connection I'll tell you when I can finish will be so this is a connection between hypergraphs and so if you have for example I1, I2, IL. This could be an edge in the L uniform hypergraph, right? So this is a subset of N. This is an edge in the hypergraph. Then you can also define the so-called exterior product using this. This is EI1, EI2. If you want, you probably need to put the dual here, but to be precise, if you want to be precise. So this will be a elementary, some people call it L vector or something. So this will be then using this construction, you can start from hypergraph H, which is a subset of N to the L, to build the corresponding subspace in so then there's a basic fact or something we proved, that is the chromatic number of this hypergraph. Here then you can define the EI space for H. EI space for H basically means that it's a multilinear function, right? When you restrict to this subspace, it becomes zero map. So then the fact is that you can also have this connection. the independence number of a hypergraph and the totally-isotropic number of this linear space of multilinear skew symmetric functions are the same. So all these, there are also, okay, then there are also connections between directed graphs to matrix space. So we have seen the bipartite graph and matrix space connection, right? So for directed graph and matrix spaces, basically then the underlying symmetry will come out. Because for bipartite graph, the left and the right vertices, they are not identified, right? But for directed graph, there's only one set vertex set. So, but how this identification or not come into picture for matrix spaces will be considered, are you consider matrix space under left, right, or are you consider matrix space under, say, conjugation action? So then for example, with RV and RVU and Ina and Fanti, we can, for example, the cyclicity, which is a more proper directed graph concept, can be going to the unipotency. Then they consider matrix spaces, every matrix should be unipotent. So all these connections, there are many such connections to be discovered and are discovered or will be discovered, hopefully. And it will lead to, by put some graph-theoretic thinking, graph-inspired ideas and techniques, hopefully we are going to solve more problems. So yeah, I guess that's it. Thanks so much.
Any questions? I want to ask you.
Yeah.
So in many of these last things you showed, alpha of G equals alpha of M. Oh, I forgot that.
Alpha of AG, yeah.
Of AG.
Is it here?
When do you expect it to be?
There are cases this may fail. Yeah.
But then it might also be interesting, right?
Yeah.
It's not necessarily a failure, it can be like I don't know. In some cases where the matrix space is richer.
In general, when we do this embedding, and also because of time, maybe I can give another when you are free. But the thing that there is, for example, also expander stuff I didn't touch, which can also go from the graph setting to the matrix space setting. In the matrix space setting, when we do this, embedding, right, from say M edge N vertex graph, we will go to a M dimension, right, matrix space of size N by N. So usually they are like kind of special matrix spaces, right? They are more special. But on the other hand, they are definitely very important examples. And for these examples, usually we have such equality and so on. But in general, for matrix spaces, there are several intuitions. For example, from one matrix is one edge is just connecting two vertices. So it's not very powerful in a sense. So usually you expect the behavior to be more interesting when you say have at least n edges or something. But for matrices, usually the idea there is that one matrix is already powerful. Two matrices sometimes still manageable, like these pairs of alternating matrices, skew symmetric matrices. But three matrices, then suddenly a lot of things already is pretty rich, and the connectivity and so on also have connectivity, and vertex edge connectivity I didn't touch, but there are something like that. Then a lot of things when you have just constant number of matrices, for example, in the expander sense, you already have expanders in the matrix space setting. If you just have like, I don't know, 10, 100 matrices, constant number of matrices already give you a lot of connectivity and so on. So things are different, but all these notions, many of the notions are inspired by graph theory, right? So including not just questions, but also techniques. So I assume that hopefully there are more things to be discovered.
Yeah, I was going to ask about the spectral thing, but he kind of said it.
Any more? Okay, great, thank you.